Michał Szczepanik, and he's working in the research center in Jülich and has a background in neuroinformatics, studied in Poland and worked on fear conditioning in neuroimaging, and then migrated towards the more data management side of this type of research, which brought him here eventually. And currently he's working on research software development in that context, working on data-led, fixing the many bugs it has and continues to produce, user support and technical writing. And he's going to talk about compute on demand, which apparently is a very well discussed feature, not only of Git Annex, and we'll hear about it.
Thank you. So if you have been around Git Annex, or if you listened to the previous two talks, you probably came across the term special remote, and you have likely started to associate this term with something that you can interact with to send your files to or get your files from. But the DataLab handbook cautions us that we shouldn't envision a special remote as merely a physical place or location. A special remote is first and foremost a protocol that defines the transport of the files to and from. And yes, this protocol would be usually a protocol for download. So if we get files, more often than not, we download them from something like S3, that's an S3 remote, or we're using a WebDAV special remote to download things from Nextcloud, and it really is download, and it really is a sort of place. There are also more, let's call them exotic things, like the archives and archivist special remotes in DataLab, which do not do any downloads. Their job is to extract files from an archive. And there was a question asked last year, but by some people who are here in the audience, is it possible for a special remote to pull things from thin air? So more specifically, to rerun the original computation that was used to create that file. And I guess it might have even been a lunchtime conversation here in Distribits last year. And the answer was yes, a special remote is an implementation of a protocol, so it can do whatever we want it to do. And what came out of it was not just one implementation, but actually two. One by Joey Hess that's built into Git Annex and is called Git Annex Compute. And the other is an yet unreleased DataLab extension called DataLab Remake that came from the psychoinformatics group at Jülich, so that's the group I am in. And these are the two that I will introduce and compare in the talk. However, I have to mention that there's also prior art in DataLab getExec by Matthias, and as far as I know, that's the protoplast. I won't talk about it in the interest of time, and also because it takes a slightly different approach. But first, credit where credit is due, and Joey gets a double credit, I guess, first for Git Annex as a whole, and then for Git Annex Compute. And then for DataLab Remake, this goes to the psychoinformatics group. We do our best to work as a unit. However, it was Christian, Gosia, and Michał who had the most input to the work, and we have received funding from the eBrain Health project. At this point, you might be wondering, well, is it the case of scientists being too preoccupied with whether they could? So there's this old adage, storage is cheap, right? And yes, but also maybe no. And for sure, in any given context, storage is limited. So for example, in our institute, it is by design that if you request some storage space on our internal cluster, part of the procedure is our sysadmin coming to you and staring deeply into your soul, forcing you to think whether you really need those 2 terabytes. Maybe you could do with 1 instead. So the storage, we have to work with limited storage in many situations, and there are also contexts where it is quite reasonable to recompute the file instead of storing it. So maybe you want to provide data in alternative file formats, like you store CSV because that's nice, but you provide XLSX on demand because that's popular in some communities. Or maybe you have one large data file, but you want to render a part of it, for example, cut a slice in the video with or without re-encoding. Or the two examples that I will talk about in more detail, you might apply some edits to a photo. So for example, you store RAW and export JPEGs based on some processing steps that were recorded, or maybe you want to apply spatial transformations to fMRI image. So in talking about the two implementations, it's useful to have a small example that helps us grok how they work. So don't worry, we'll do fMRI at the end, the thing that I promised in the abstract. But first, let's do something simpler. So recently, I have been having fun with film emulations. So you take a digital photo and you apply a color lookup table to it. So you remap pixel values to different pixel values, and people have done lookup tables that make things look more like some old and well-known film stocks. So in here we have a photo of Düsseldorf on the left. We are using gmic as a program that implements these things nicely, and it's a very simple command. You use gmic, you give it you tell it you give it an input, and you give a name of the input file, and then you tell it to map it through a color lookup table, and you give an example like the emulation of the legendary Kodachrome, and then you say what the output file is, where it should put it. So we'll try to do this with the two special remote implementations. First, git annex compute. By the way, there is an excellent introduction tutorial to git annex compute in git annex documentation. I'll do something similar but slightly different here. So Joey tells us that we need to write a compute program, and the official tutorial uses bash. I'm terrible in bash scripting, so I will use Python, even though it's extra steps. Well, first of all, it's a program. It's given a name that has to start with git annex compute, and it has to be placed somewhere that is in our path, so it must be executable. And it can take arguments, so it takes arguments for whatever we want to feed into it. So in these things, these are the things we need to fill in. So input, output, and the color lookup table we are using. And then the program needs to follow a protocol, and the protocol is we talk over standard input and output. So in our program writes uppercase input, and then it writes what file it wants to, the file name of the file it wants to receive as an input. And then our program reads standard input, and there git annex gives it the path to the annex object that it has stored, or I guess git object if that's a git file, not annex file. And it can do this because it already tracks those, and it also can do it in a smart way. So if the goal is to reproduce what we have calculated, then we need to start with the state as it was as we wrote the specification, not with the current thing that is under the file name. And again, that's something that git annex does a good job tracking, so it gives us the path to the file in git annex objects. And we do a similar thing with what we want to write out. So we say output, and we say what's the file name for the output, and git annex responds to us with the path where to a temporary location where we should place it, and then git annex will come and collect it. And then our program can do whatever it wants. So here I'm doing a very simple thing. So I'm starting a subprocess to run gmic and fill it with either the things that I received from git annex or the things that I received as direct parameters to my compute program. So in action, we might need to do some preparation. So it's not necessarily if we are creating this, but if you want to use this again from another location, we need to fill in the allowed compute programs configuration. So as a layer of protection, we don't want to be running things we don't want to be running. So it's a global git configuration, plus you have to follow this naming pattern. And then the usage is simple and just like another special remote. So initialize the remote, give it a name, say it is the type compute, and you give it the name of the program that will be running behind it. And then you run git annex add computed. You can give it optionally an option fast, which means don't compute now, just record that it will go through this remote. You can give it a flag reproducible, so mark that you are expecting it to come back with the same checksum every time. You have to say to which compute special remote you are adding this, and then you are giving it arguments that go directly into your compute program. So file, input file, output file, lookup table. So let's do the same thing with data remake. Data remake takes a more declarative approach. So you don't write a compute program, you write a compute template. And in the compute template, you specify basically the same thing. So you start with what are your parameters. So what will be variable between files, but same for this, the same for this template of computation. In this case, we have input file, output file, and the lookup table. And then we can say what is the command that we will run, and this is in the format that would be given to subprocess. So in my case, it's exactly the same gmic input and one of the parameter map c lookup table and the lookup table and output. In more realistic scenarios, it would, for me, it would be probably Python run some sort of code that I have in the dataset. In action, this is again similar. We have some prerequisite, a different safety mechanism. So so this thing also goes to data.make methods, and the name is of your choosing. And when you commit that in the dataset, so we're expecting you to commit this file into the dataset, we are also expecting it to GPG sign the commit, and then in your global Git configuration, you store the list of trusted keys. So if it's signed with a trusted commit, it can be, if the commit is signed with a trusted key, the thing can be executed. And then, we've written the template, we are saving it and signing, and then we are running a data.make command, again signing the commit that it will produce, and we specify the input file, the output file. So the input file is what needs to be provisioned in advance. The output files is what we would produce, and then parameters, which are things that we will be filling in the command template. So we are repeating the things essentially here, and one parameter is something that we can vary, is the color lookup table if we want to have several. So what does, we can look into this in a little bit more detail. So what does data.lad record from that? So first of all, when we run data.make, it commits another file, it's called specification, and it's saved under a name that's a checksum of its contents, so git annex style again. And it contains a combination of the things that we have provided before in the template and in the parameterization of the make command. So we now have recorded what is the input, what is the output, what are the parameters explicitly, and what is the method. The method points to a file name, which is not a problem. Why? It still has very specific meaning. Why? Because we associate this specification with the file through a git annex URL. So we can git annex add URL to a file, and we have our own prefix data.remake, which then gets claimed by the remake special remote, and it stores the following things. So label is the compute template that would be using. The root version is the root version of the dataset that, so the SHA of the commit at the point at which we created this specification. The SHA-sum of, I think SHA-sum, or MD5 sum of the specification file, and this means which file it attaches, so it's good to have it here as well. So with this information, again, data.lad can go back to the state it needs to reproduce the file exactly. How it does it in a second. So let's compare the two approaches. So the idea is the same, the implementation approach is different. So first of all, we have different way of specifying what we want to do. For Git Annex, it's a compute program, and this has to follow a specific protocol. And for Data Remake, it's a configuration approach. You have to have a compute template. So where the information gets stored, for Git Annex, it keeps all its things in the Git Annex branch. With Data Remake, we make you commit things to your main branch or current main branch. Plus, we are storing a Git Annex URL to connect the files with the template. Now, provisioning, this is an important step. I've covered this for Git Annex Compute, where the special remotes provides paths to Annex objects. Data Remake does provisioning with extra steps, so to say. So it creates a secondary Git worktree in a location of your choosing. By default, it goes into temp because it's meant to be temporary. So it creates a Git worktree. So usually we have .git and all the worktree right alongside, but we can have another one somewhere else that's built into Git, and we can tell Git to set it to a specific commit. So that's where we are using the information about the commit, and that's how we start with a specific state. The trust model is different, so for Git Annex we need to have an executable in path and a Git configuration. For Data Remake we're using signed commits and a Git configuration. Now the usage differences are the two biggest, I think, are first submodules. So for Git Annex, it operates with the assumption that you have one repo. So you're asked for a path, and either the Git repository has a file under the path, or if it's in submodule, it's not there, and we cannot do this. Data likes to work with subdata sets, and in the work tree, in the separate work tree, things work very similarly. So you can datalat get a file, and then it will get the subdata sets it needs, traverse the path, etc., etc. And finally, for Git Annex Compute, you have the option of being reproducible. For datalat, this is the only way you can go currently. So you might be thinking, what about datalat run and rerun? They also redo some computation, but there's conceptual difference. So first of all, run records store information in commit messages, make stores information in file, and run records are used by rerun, so there's a dedicated command. For make, it's sort of hidden beneath get, so it's meant to feel like a slow download. Datalat run make commit, make spec, make just reproduces the file. We're using temporary worktree for make, and we are using branches for run records, but by default you're working on top of what your current head is. So a different purpose for run record is provenance capture. For make, it's more storage reduction and maybe more focus on a single file than on a single processing step that produced multiple files. So now let's do some real-world usage with fMRI. So in functional MRI studies, we have this big and loud machine. We put a person into the machine and give them some task. We acquire continuously some images over time, and the problem that we have to solve often is of spatial normalization. So just like our brains are, our faces are different but similar, our brains are also similar but different, so things are roughly in the same place. So you have to apply some spatial transformation, and it takes time to compute, but what you produce is small to store and quick to apply. Our enables, and that's a small and quick love letter to the community. Bits is a standard for file organization and metadata storage in sidecar files, and fMRI prep is a piece of software that does this thing as one single step, but it's also really modular, so you can take the transform and really apply them quickly. So after running fMRI prep, you get a layout that looks like this. Usually you organize things so that your inputs are in a subdata set, and your pre-processed file that you've processed can be like in the order of 400 megabytes, and their transformations are under 100 megabytes. So you have room to save here. And I have a demo online for you to explore. So just very quickly, these are the files we're interested in. The code is made simple by the modularity of fMRI prep, so you can apply a single import a single workflow from fMRI prep, and then your job is to figure out the dependencies. That's easy because you walk the tree, set up the workflow, connect inputs, outputs, run the pipeline, and tweak the file header because some things come out differently and we want it to be bit reproducible. So it took about 360 lines of code. The compute template has one parameter, that's the target file, because you can discover from bits what other things you need. The command is Python code to run this resample script that you have written. A pro tip is to pin your dependencies like really strictly. fMRI prep is a large code base, but maybe ideally use a container. The actual data dependency list is quite long, but again can be generated automatically. You don't have to save it. You pick a target, you run data.make. One thing, so you're coming into a already prepared file. So one thing you could use is prospective execution. That's the equivalent of fast. So you're not doing the computation right there. You're just saying that this computation can be done because you have the file at hand already. Fill in input-output parameters. Then you can data drop the thing that you get, and in a few minutes you should have the file back. Was it worth it? Per single file you can save 300 megabytes, but multiply this by several output spaces that people like to say, and by several runs that people usually do in the experiment. So for an average project, you're saving like 0.1 terabyte maybe, which is, well, maybe not huge, but a good chunk of your project space that you have negotiated for. Remake has some limitations. I find it hard to debug. The fMRI prep example works because it's really nice in that way. Many-to-many is not efficient. If you have declare two output files and get both of them, they're gotten one by one, so it repeats the whole process twice, at least now. And I think we had some initial ambitions with aligning with common workflow language and using more metadata and being less reliant on Git that we don't do. Key message to implementations now, still room for further development. We should all praise fMRI prep for how reproducible and modular it is. And yeah, you should have fun with your remake examples. Thank you.